for imaginary numbers. It's a new concept they bring up in 0320. It's a little different than from Math 0310. Let's go back, if you did take a Math 0310 course, and you came across problems that said like minus the square root of negative 36, what would you have put for an answer?
Negative 6.
Recall?
Negative 6?
You would say that's not a real number.
Yeah, because 6 times 6, the only thing, okay, it's like factoring, because like 6 times negative 6 is 36. And
Yeah, so
square
you
root
would-
of something is something times itself.
So if you were in Math 0310 and they gave you a problem square root of negative 36, you would say that's not a real number. Well, it can't be negative 6, right? Because negative 6 times negative 6 is a positive 36. So the square root of negative 36 can't be negative 6. You just say not a real number. Well, when you get to Math 0320, they're like, well, let's explore this concept a little bit further and introduce imaginary numbers. Because if it's not real, it's imaginary. So we're going to talk about imaginary numbers today. And you might be asking yourself, well, I have a hard enough time with the real ones. Why do I have to introduce imaginary numbers? There actually are some real-world applications for them. Electronics uses them. How many of you have a cell phone? Right? Everybody, right? How many of you would die without your cell phone? I would, right? I need my cell phone for a lot of things. Well, imaginary numbers are responsible for satellites, telecommunications, cell phones, various different things that you might not think they're used for, but they are. And on the back of that first page, there is a little paragraph about why do we even need imaginary numbers. And you can see it kind of shows up in different parts of science, even biology, chemistry. So there are some practical applications for them. The back of the page, the first page, also includes some definitions of what an imaginary number is, some operations that you use for them, and we'll kind of refer back to this as we're working through some of the problems. So we have some problems here, and so the top of the second page, it says simplifying expressions involving complex numbers. So let's say I have the square root of negative 9. We said back in Math 0310, we'd say, well, that's not a real number, and you jump the problem and move on to the next one. But in Math 0320, we're going to say, well, let's define some things here. I could break up negative 9 into negative 1 times 9. Is that still correct? Well, as one of our definitions, the square root of negative 1 represents the letter I. It stands for an imaginary number. So, if I have negative 1 times 9, the square root of negative 1 is I. Well, what's the square root of 9?
3.
3. So this would just become 3I. So you're basically taking the square root of the number like you normally would. Square root of 9 is 3, and you're just attaching an I to it to represent that it's an imaginary number rather than a real number.
Like what number would it take to make this a true statement?
Mm-hmm. Very true. So the next one, square root of negative 11. Well, I can break that up into negative 1 times 11. Can't really break up 11 any further, right? It's not a perfect square. So in this case, what's the only thing that would come out of the square root here? What's the only thing that would come on the outside of the radical? What's the square root of negative 1 represent?
I.
I. So I know that I is going to come out. But can I take the square root of 11? No. So that's just going to stay inside. So there's different ways of writing an imaginary number. We still follow our rules for simplifying radicals. But the fact that it is imaginary, because we have that I on the outside.
So you only put it next to the number if it's the square root of the number?
Yes, if we can pull the number out, It'll come in front of the number. If it
Okay.
stays in the radical, it's gonna stay behind.
Gotcha.
Which brings us, very good question, to our next one, which is -80. Well, I can split that up into, let's take the -1 out first. Now, 80 has a whole list of perfect squares that go into it, right? We have 4 goes into 80, that's a perfect square. 9 doesn't, but the next perfect square, 16, does 16 go into 80? How many times do you think 16 goes into 80?
No, 5.
5. 5. So we could write 80 as 16 times 5. Break it up into a perfect square. So how do you think we'd write this one? What could come out of the radical? Square root of -1 is I. Square root of 16 is 4. So a 4i would come out. And I still have that square root of 5 left over. So break up the radical like you did, in 0310, or if you're working with them in 0320 as well. You're just attaching the I there to represent an imaginary number. The process for simplifying them is still the same. The next one there, let's say we have two radicals. One is -4, and we're multiplying it times square root of -36. Okay. So we've kind of simplified some of these radicals here. What's the square root of -4? What would that be?
2 times -1.
2. We kind of get past this kind of baby step here. What's the square root of 4?
2.
So the square root of -4 would be 2,
Times 2 times -1.
2i. Has to be imaginary. Have to attach the imaginary number there.
Even though it's negative?
Well, the square root of -9 was 3i. right?
Okay.
The square root of a negative number is just represented by an imaginary I right there.
Okay. So 2i times 6i.
There you go, perfect. Square root of 36 is 6, so the square root of -36 would have to be 6i. Now we can multiply those together.
Would it be 12ii?
12ii. Are you on a naval ship, Captain? So if I multiply, think of this as, what if this was x? What would x times x be?
I squared.
Be x squared, so I times I will be
I squared.
I squared. So let's go back to our definitions on the back of that first page. And where it says powers of I, notice I to the first power, I is just I. I squared is what? It says I squared is equal to -1. So we're going to replace 12, or 12i squared, with 12 times -1. What's 12 times -1?
-2.
-12.
So that's the final answer?
That's the final answer. Something interesting here. I have an imaginary number times another imaginary number. And I end up with a real number. It's weird, right? So there are ways to use imaginary numbers to get real solutions. So they do come into play. So we've come across another definition, I squared is equal to -1. So that's simplifying radicals involving imaginary numbers. Let's move into some operations involving complex numbers. Are we good on these? Leave those definitions up there.
So 4 times 6 is 144.
Mhm.
12 times 12 is 144.
Yep.
But then signs don't match that.
Well, you have to simplify square root of negative 4. You have to make that into an imaginary number first. Right? You can't do negative 4 times negative 36.
So if you're multiplying numbers, will the answer always be that times itself? Will add up to that even if the sign's different? Like a double check method?
In order to work with complex numbers, they have to have an I involved with them. So if you're doing an operation, it can't be in radical form. You have to put them in imaginary number form first, and then work with them.
Right, what I'm saying is that like, since 12 times 12 is 144 and 4 times 36 is 144, will the final answer always be times itself? Like, to the original problem, you multiply those numbers and then the answer times itself is?
I would not do that.
Okay.
All right, so the next section says finding real numbers using complex numbers. So let's say I have 3x plus 4i, and that's equal to negative 6 plus 12y I. A lot of letters, few numbers. What does it all mean? So a complex number and this is also defined on the back of that first page, is something that's written in this form. A complex number has a real part and it also has an imaginary part, the part that involves the I. So basically a complex number is a real number plus an imaginary component. So if I had something like 3 plus 4i, that would be a complex number. The 3 would be the real part, the 4i would be the imaginary part. Okay? The only way two complex numbers can be equal to one another is if the real parts are equal. Okay, that's the real part. Everybody agree with that? That's the real part. And the imaginary parts have to be equal. So I can set up two equations here. The only way these two can be equal, well, the real has to be equal to the real part. So 3x has to be equal to negative 6. In order for the imaginary parts to be equal, and we really don't even need the I here, we just need the coefficients. 4 has to be equal to 12y.
Can we keep I there?
You can, but it's not really necessary.
So you get factor.
No. We're just going to solve these. So I have 3x equal to negative 6.
Negative
That's just a
2.
little simple equation to solve there. So x equals negative 2. What would I divide both sides on my second equation by to get y?
4.
Not 4. We're trying to get y by itself, so we're going to divide by 12. So that's going to be a fraction, right? What's 4 over 12? What does that reduce to?
1/3.
1/3. We got another example to follow there. I know that's a little bit out there as far as the concept. Now somebody asks, can I put my eyes in there? It's not wrong, but I'm going to show you that it really doesn't matter that the eye is there or not. Let's say I have x, don't laugh, smiley face, equal to 3, smiley face. What would x have to be equal to?
Right.
Okay. X has to be equal to 3. Does it really matter if the smiling face is there or not?
No.
Okay. That's why we're only really interested in the coefficients there. The I really doesn't matter. We're just interested that 4 has to be equal to that 12y. Because if you put the i's in there, you're going to have to cancel them out anyway. So don't make fun of my smiley face equation.
Well, I was just thinking one was smiley face, one was frowny face.
It's 2 different things. You can do it. But we have the same thing there. We have guys are the same. So let's try another one. Six plus x minus 3i equals 13 plus y I. What part do you think is the real part on this left side?
6.
6 plus x, the whole thing right here. Because the imaginary part is just going to be the part that's attached to the I, which is that negative 3. So 6 plus x has to be equal to 13. As far as the imaginary part,
Negative.
yep,
3.
negative 3 has to be equal to y. That's easy enough. We already got y. Negative 3 equals y. So we only have to solve this other equation for x. And how would I do that?
Subtract.
Subtract. So 6, right? So x ends up being equal to 7. X equals 7. There's my 2 answers for x and y. I'm getting a face that maybe you don't believe me, right? All right, let's check it to see if it works. So let's go back to our original complex number, 6 plus x minus 3i equals 13 plus yi. Let's plug my numbers back in. 6 plus 7, the number we got for x, minus 3i equals 13, and then in place of y, we're going to put minus 3i. What's 6 plus 7? 13. So 13 minus 3i equals 13 minus 3i. Do I have the same thing on the left and right side? It works. All right. We're just finding the values of x and y that will make a true statement using what we know about complex numbers.
So if it doesn't look like that, do you have to rework it, or do you just say?
Yeah, if you go to the check and you have something different, that means you worked something out wrong over here.
So to these, it will always be a true statement?
Yes. Well, that's what
Because it's
equal-
imaginary.
Well, that's what an equal sign means. The left side has to be equal to the right side. Thank you.
I'm sorry.
Are we good there?
Oh, we're perfect.
All right. So let's talk about some powers of I. We already have some definitions. Let me erase this over here. And these powers of I are also listed on the back of that first sheet. Well, anything to the first power is just itself, right? So I to the first power is really I. I to the second power is -1. I to the third power, if you work it out, ends up being -I. I to the fourth power equals 1. This list actually keeps going. You can work it out algebraically. I to the fifth ends up being I to the sixth is -1. I to the eighth, or I to the seventh, sorry, is -I. I to the eighth is 1. I to the ninth ends up being I. What do you notice what happens every 4 powers?
It turn to a positive.
It starts repeating, right? We're only interested in these 4. It just repeats over and over and over again.
The cycle of I.
Yep, cycle I. So it just starts repeating, so we're just going to focus on these four. So let's say you were given a problem that says, well, I need to know what I to the 31st power is. Well, I don't want to write out 31 powers of I and figure out what it is. Let's use this pattern to figure it out. What's 31 divided by 4? We're only interested in 4 powers. So let's take this power and divide it by 4 and see what happens.
7 with a remainder of 3.
Okay, 7 times 4 is 28. And I get a remainder of 3, correct? Does everybody agree with that?
It says 7.75.
That's why the calculators are going to help you here. Because we're interested in a whole number remainder. And we have to reach in our bag of old school arithmetic and do long division by hand. 7 times 4 is 28. We get a 3. The remainder is the key here. That's going to tell us what power of I is. So I to the 31st means the same thing as I to the 3rd. And from our chart, I to the 3rd is what? Negative I. Now that's where I answered you. So we're basically simplifying these huge powers of I using this chart here.
So what do you do with the remainder?
The remainder tells us what power of I is. I to remainder of 3 means this really means I to the 3rd equals negative 1. So, and this is also on the chart, on the back of the first page. I to the 1st will have a remainder of 1. Remainder 2, remainder 3. And if I'm dividing by 4, can I have a remainder of 4?
No.
No. So I to the 4th will have a remainder of 0. Okay, so let's keep that chart in mind. Let's move to the next one. I have 4 of them, so we'll get some practice here. I to the 48.
1.
I to the 48.
You always divide by 4, right?
Always divide by 4 because that's the length of our cycle. We have 4 powers. So 4 can go into 4 one time. Bring 8 down. 4 can go into 8 2 times. I get a remainder of 0. So looking at our chart, I to the 48 is equal to
1.
1. Not so bad, right? Another we're going to laugh at Kurt moment is coming up. An easy way to remember this chart if you're ever having a hard time remembering these powers, well, think of it. There's I and negative 1, negative I and 1. I won. I won,
I want to see
right?
you jump when you do that.
I'm not jumping. Just gotta remember that the middle 2 are negative. But if you can remember that phrase, I won, that will help you kind of remember the order that the powers go in. Okay?
Good.
All right, so we got a couple more of the power ones to work out. We have I to the 17th power. So once again, we're just going to take that power and divide it by 4. So 4 goes to the 17 how many times?
4.
4. 4 times 4 is 16. What's our remainder? 1. So I to the 17th from our chart really is just equal to I. Exactly. There you go. Piece of cake. The last one, had to do it, had to give you a big power, 242. So I to the 242nd power, we're going to take 242 and divide it by 4. 4 goes into 24
6.
6 times. 6 times 4 is 24. 0 and 2. How many times can 4 go into 2?
Can't.
It can, so we have to put a 0. 0 times 4 is still 0. We're still left with a remainder of 2, correct? So I to the 242nd power is really equal to
Negative 1.
60, negative 60.
negative 1. It can only be one of these 4 things. The remainder of 2 tells it it has to be negative 1. We're only interested in the remainder. It's your only 4 choices. I want, right? It's your only 4 choices. So that's how you deal with powers of I. Just divide it by 4, and then use the remainder to tell you what it will reduce down to. Not so bad. Well, complex numbers you can work operations with. Addition, subtraction, multiplication, and division, just like other numbers. Right? They still work along the same way. So, let's fix that. So we have 7 minus 6i plus 2 plus 3i. We're just adding 2 complex numbers together. Well, do we really need the parentheses here? Is anything happening in front of these parentheses? And there's no number being multiplied, so we can really just drop the parentheses. They're only there in this case to designate that this is one complex number and you're adding it to another complex number. But as far as operations, there's nothing happening in front of them, so we can just drop them. Complex numbers, you just add like terms. You can only add real numbers together. You can only add complex numbers together. So 7 plus 2 is what? 9. And then I have negative 6i plus 3i. Negative 6 plus 3?
Negative 3.
Negative 3. Just make sure you got the I with it. And that's how you add complex numbers. You just add the real parts together, add the imaginary parts together.
And you don't reduce or
Is that factor your answer?
That's it. It's just like adding like terms back from, 0310. You're just adding like terms together. Not so bad. The only thing I will say is your answer has to be in this form. It has to be in that standard form where the real part comes first and the imaginary part comes second. So is our answer in that form? Does the real part come first? Yes. So it is in that form, we're good to go. That's all you have to worry about. Okay, so that's how you do addition. So let's talk about subtraction, which is our next problem. We have negative 3 plus 2i. And we're subtracting negative 5 minus 3i. There's only one little twist from addition. Is there anything happening on this parentheses? Is there anything being multiplied times this one? No. But we do have to worry about this negative sign for the second parentheses. Think of this as a negative 1 right here. And what would I be doing with that negative 1 in front of the parentheses?
distribute.
Yeah, distributing, multiplying. Just make sure you distribute it to every piece inside that parentheses. So a negative 1 times negative 5, positive 5, right? And then we also have a negative 1 times a negative 3.
Positive 3.
Yep, positive 3i. And then I'm back to what I did in the previous problem. We're just going to add together like terms again. So negative 3 plus 5,
2.
2.
2. That's our real part. Adding our imaginaries, 2i plus 3i
5.
plus 5i. Is it in standard form? Does the real part come first? Yes, we're done. Piece of cake. So that brings us to our last page, which involves multiplying and dividing, which are a little bit more complex, but in the end, very easy. So we'll take a look at those. The first one involves taking an imaginary number and multiplying it times a complex number. So negative 5i times 2 plus 7i. So just like with regular numbers, with real numbers, we're going to distribute negative 5i times both pieces. What's negative 5i times 2?
Was it 10 over 10?
Negative 10i. Works just like if it was a variable. Negative 10i. And then negative 5i times positive 7i. Negative 35. And I have an I times an I there, so we had that earlier. I squared, correct. So negative 10i, can't do anything with that. But this one's a little different than when we had addition and subtraction. I have a different power of I involved here. Well, let's go back to our chart. What does I squared really mean? Negative 1. So let's replace I squared with what we know it by in definition, negative 1. So we can take that further. That's negative 10. Negative 35 times negative 1. Thank you. Positive 35. Is it in standard form? Does the real part come
No.
first? No. So we just have to reverse it. Just put 35 first, 35, and then minus 10. That's as far as that one goes. Did you go on that one? Not so bad. Did you press that? Try green. See if green shows up a little better. Yes. All right. 8 plus 5i times 7 plus 4. This looks kind of like something we've seen before. If you ever have two pieces in parentheses and you're multiplying it times another two pieces in parentheses, what do you have to do?
Take them out of the parentheses.
What do you
Oh,
think?
foil it.
Foil, exactly. Our good friend foil.
So there's no plus or minus in between.
So we have to do first, outer, inner, last. So let's do that. We got 8 times 7. It's 56. Then we have 8 times 4i. What would that be?
32i.
32i. Then we have 5i times 7. 35i. Then we also have this 5i times 4i, the last. 20i squared, very good. Can we add together these numbers?
32, 35.
Yep. 32i plus 35i is plus 67i. We can't add that I squared because it's not a like term, it's not a single I. But we know that I squared is really what? -1. From definition, I squared has to equal negative 1. So it looks like we can take this a little bit further. What's 20 times negative 1? Negative 20. Well, we have some more like terms we can add together now. We have 56 and minus 20. What does that give me?
36.
36. Plus 67i. Is it in standard form? Does the real part come first? Yes. So you should notice that all of our answers just have I, right? There's no I squareds left over, there's no I cubes. The highest power of I you should have in your answer will always be I. If you have an I squared or an I cubed, something higher than that, go back and check to see if you didn't reduce somewhere. Okay. We have one more problem in the multiplication. And that's to square it. Ahead of myself. So I have a binomial squared, 3 minus 2i squared. What do you think I should do with that?
Boil it?
I will FOIL it. Do not make the mistake of just taking the square of each piece. It's a binomial that's squared. So we have to write it twice, and then we're back to FOILing it, like we did in the previous problem. So, first, 3 times 3 is 9. Outer, 3 times negative 2i, negative 6i. Inner, negative 2 times 3, negative 6i. Last, negative 2i times negative 2i, positive 4i squared.